Hello, my name is Sunggon Kim. I am a PhD candidate from Seoul National University in Seoul, South Korea. Today, I'll present my paper called Towards HPC I/O Performance Prediction Through Large-Scale Log Analysis. This is a joint work by Seoul National University, Korea, Lawrence Berkeley National Laboratory, USA, and Chung-Ang University, Korea. Here is the contents for today's video. First, I'll introduce background of this paper, then continue with design of our paper. Then, I'll present the analysis result of system logs in our supercomputer environment. Afterward, I'll present the evaluation results of our performance prediction scheme. Finally, I'll conclude this talk with the conclusion. Here is an overall architecture of our system. For this paper, we used Cori supercomputer at Lawrence Berkeley National Lab. Cori is equipped with more than 700,000 processor cores. There are two types of cores, which are traditional Intel Xeon cores and KNI cores that have high core count and lower frequency. In terms of file system, Cori is using Lustre, parallel, and distributed file system. As many of you are familiar with, Lustre is one of the most widely used file systems in HPC community. In Cori, there are 248 OSSs and over 10,000 hard disk drives. To provide a continuous service to multiple users and monitor the system, Cori is collecting multiple system logs. Darshan log is a I/O characterization tool that collects application-specific behaviors such as job ID, start time, and number of files. Slurm is a widely used job scheduler that coordinates multiple jobs in a large system. In addition with the job scheduling, it also collects information of a job, such as job ID, program name, and number of nodes that are allocated to the job. Finally, Lustre Monitoring Tool, also known as LMT, is a monitoring tool that collects general Lustre file system information. It collects information such as CPU usage of metadata and data servers in a 5-second interval. The figure in the right bottom side shows the availability of logs in the perspective of application execution. When an application is first executed, the requested resources are first delivered to the Slurm for resource allocation. Thus, the information from Slurm is available at the start of application execution. In contrast, LMT information is generated in a 5-second interval, and the complete information is available at the termination of application. Similarly, Darshan information is collected at the end of the application. The availability of logs is crucial when predicting the performance, since the prediction is made at the start of application execution. Thus, it is important to know which information is available to predict the I/O performance. When we first started the project, our goal was to predict the I/O performance using the existing information in the system. By predicting the performance, we believe that we can improve the resource management efficiency and reduce the performance degradation due to contention. To do this, we divided features into two categories, such as application characteristics and file system characteristics. Application characteristics are features that are limited to the target application, while file system characteristics are status of global file system when the application is running. For the target metric, we have selected write and read throughput, which are the performance metrics. This slide shows the overall algorithm of our proposed scheme. Our scheme follows a traditional performance prediction scheme. We first build an integrated database from various system logs. Then, we select a few I/O characteristics that are most relevant to the target metric. Then, we build a model using the selected features and the training data. Finally, we make a prediction using the model. Let me explain each procedure in detail. In the data preparation phase, we create an integrated database for system logs which are mentioned in the background section. We first parse the data from various system logs. Then, using the job ID as an index, we create a SQLite-based integrated database. This is to select a large amount of information in a fast manner. With the integrated database, we then proceed to the feature selection phase. To select the most correlated features from many features we have, we use the Pearson correlation coefficient. This is a statistical approach that measures the correlation between variables. By using the Pearson correlation coefficient, we can find the correlation between the target metric and various features in the log. With the selected features, we continue with the training and the prediction phase. With the selected features and the target metric, we build a model and make a prediction using the model. For the model, we use various regression algorithms to see how each algorithm have different accuracy. For the traditional statistical regression, we have selected linear and polynomial regression. For the ensemble approach, we use k-nearest neighbor regression and random forest regression. For recently widely used multi-neuron regression method, we use MLP regression and CNN regression. We will present how different regression algorithms react differently in the evaluation section. This slide shows how we create a model using a linear regression algorithm. As we can see, a model is a simple mathematical equation. The target metric, in this case, the write throughput, is represented by coefficients and features. Based on the training data, we determine how each features are related to the write throughput and devise an equation. In the prediction phase, we use the model created from the training phase to determine the write throughput of new incoming application. Although we covered the general scenarios of our proposed prediction scheme, there are a case we must consider. As mentioned in the background section, some information can be unavailable. This means that even if the features are selected as the most correlated feature, we cannot use the feature since the information is not available until the application termination. To overcome this issue, our scheme performs recursive prediction on the unavailable features. If a feature is unavailable, we recursively perform feature selection, training, and prediction using the unavailable feature as the target metric. Then, we use the predicted value from the regression to perform the prediction on the target metric. Thus, our scheme can successfully perform the prediction when the information is not available. Before presenting the evaluation results, I will first present the analysis result of Cori supercomputer. This can show how we try to find the correlation between characteristics and performance and come up with the idea presented in the design section. For the analysis, our goal was to find correlation between I/O characteristics and the performance. To find the correlation, we categorize features into application characteristics and file system activity. We analyzed each characteristics and see if each characteristics has clear positive or negative correlation with the performance. For the data, we use data from Cori supercomputer from Berkeley lab. We use the data from October 2017 to January 2018, and there are over 3 million application execution history during the time period. Note that each application execution does not mean there are 3 million unique applications. If an application was executed 500 times, then it will create a 500 different application execution history. This slide shows the correlation between application characteristics and the application write throughput. Left figure shows the correlation between request size and write throughput. As data points are located in left, it means that that application has small request size. And the right figure shows the correlation between the access pattern and write throughput. As the data points are located in left, the application has more random access pattern. In a local file system, we always assume that if application has small request size and random access pattern, it has low performance compared with the application that has large request size and scheduled access pattern. However, as shown in the figures, we can see that there is no significant performance trend difference between small and large request size applications and random and scheduled access pattern applications. This results suggest that individual application characteristics does not have significant impact on the performance. In this slide, we present the correlation between file system activity and application's performance. Left figure shows the correlation between CPU usage of metadata server and application's performance. And the right figure shows the correlation between data server's write throughput and application performance. In both figures, as the data points are located left, it means that there was no activity in metadata and data server. As shown in the figures, we can see that there is no significant performance trend as the file system becomes more busy. However, if we focus on the right figure, there is a positive correlation between data server business and the performance of application as data server writes more data. We will focus more on this positive correlation. In this slide, we look at the data server activity when an IO-intensive application is running. Each line in the figure denotes each OSS server. As the color becomes red, it denotes that the specific OSS is busy at the time. When an application, in this case IOR, is running, we can see that every OSS is utilized heavily and OSS is relatively free when the IOR is completed. This suggests that when an IO-intensive application is running, the data server activity is dominated by the specific IO-intensive application. To verify our observation, we look at the correlation between data server activity and write throughput again. However, in this time, we focus only on the IO-intensive applications. As shown in the figure, we can observe that there is a positive correlation between the data server activity and the application performance when the high IO intensity applications are only focused. This suggests that when IO intensive applications are running, the overall file system activity is dominated by that application, and we can predict the IO performance by looking at the data server activity. Although there are more analyses in the paper, we will conclude the analysis with key takeaways. First, there is no single IO characteristic that is dominant enough to observe a clear correlation between the write throughput. This suggests that HPC systems have a very complex IO performance model. Second, there is a strong correlation between the OSS activity and the application write performance in a IO-intensive applications. This result suggests that by looking at a certain group of applications, the IO characteristics can be used to accurately predict the IO performance of applications. In this slide, we present our evaluation result using the proposed scheme. For the data, we used the identical data set from the analysis section. To determine the prediction accuracy, we use coefficient of determination, often known as R-squared. This is widely used to determine the accuracy of the prediction algorithms. For applications, we used a group of high I/O intensity applications, a group of medium I/O intensity applications, and targeted few specific applications. This slide shows the prediction results of high I/O intensity applications. The table shows the combinations of regression algorithms and their coefficients of determination. The first algorithm is the algorithm used to predict the unknown features, and the second algorithm is the algorithm used to predict the target metric, which is the right throughput in our evaluation. As shown in the table, we can see that a combination of linear regression and random forest regression has the highest prediction accuracy of 0.84 of R-squared. We will present how each combination of algorithms has different prediction results in the next slide. This slide shows the prediction result of combinations of algorithms listed in the previous slide. Top 3 combinations have the best accuracy, while the bottom 3 combinations have the worst accuracy. The y-axis shows the predicted result, while the x-axis shows the actual measured accuracy. As the data points are placed at near the black dotted line, it means the prediction was more accurate. As we can see at the top 3 figures, our proposed algorithm can accurately predict the performance in high I/O intensity applications. There are also interesting results in the bottom 3 figures. Although the accuracy is similar on all 3 figures, we can see while the first and third figures have very poor accuracy, second figure seems to have done better job at predicting the I/O performance. However, since the accuracy is determined by the average difference between the predicted and measured value, R-squared cannot be used as the absolute indicator on prediction accuracy. This slide shows the prediction result of medium I/O intensive application in a similar format. As shown in the figure, we can see that the prediction accuracy is much lower than the high I/O intensity application. This is because medium I/O intensive applications have more diverse characteristics than high I/O intensive applications. Since each factors impact the I/O write throughput in more diverse manner, it is hard to predict the performance when the applications have more diverse characteristics. To control how each factors impact the write throughput, in this slide, we present the results of targeting specific applications. For applications, we have chosen a quantum chemistry application and 2 biology applications. As shown in the figures, we can see that the prediction accuracy is improved compared with the medium I/O intensity applications. This is because each application has distinct I/O characteristics, and thus the model created in the training phase was more accurate. Since the model created in the training phase was more accurate, the actual prediction result is more accurate than the result of medium I/O intensity applications. In conclusion, our work was focused on creating a comprehensive understanding of system logs by creating an integrated database. Then, we analyzed a large HPC system in the perspective of application characteristics and file system activity. Finally, we performed the performance prediction using the history of applications and various machine learning algorithms. Thank you, and this is the end of our presentation.